When you hear about the term AI, people think about the movie-driven idea of AI, where it's something that approximates human intelligence. And today, there is not even a roadmap to getting to something like that.
What does deep learning look like for you? So often we think about what deep learning means, what it does, but how do we visualize it? What does deep learning look like? Maybe your mind draws a blank. Or maybe it jumps straight to the Terminator, The Matrix, 2001: A Space Odyssey, iRobot, or your favorite Black Mirror episode. But what if deep learning concepts and the future of AI could be visualized to help make them more accessible, to help make your mind form pictures about complex concepts so you can better envision them? Deep learning has the potential to augment every aspect of our lives, but not necessarily in the extravagant or dangerous ways our minds might think. Just as Google search made it easier to pull an answer from the internet, or Alexa makes it easier to put on your favorite music, many of our future technologies will follow the same trajectory, nudging us towards slightly better information or entertainment. Today's guest is Jon Krohn, an expert in AI, deep learning, machine learning, and data. He's a chief data scientist and the author of Deep Learning Illustrated, a book that provides illustrated practical references and tutorials for developers, analysts, students, and executives who want a way to think about deep learning that's more practical. So if you're like me, you love flipping to the part of the book with pictures. His book is packed with them, and in today's episode, we do our best to help illustrate some of these concepts with our words. Whether it's neural nets, the philosophy behind this stuff, the ethical issues surrounding the future of data and machine learning, the difference between artificial narrow intelligence and artificial general intelligence, or how AI might be the paintbrush of the future, Jon and I cover it all. Enjoy.
This season of Hidden in Plain Sight is brought to you exclusively by our friends at Splunk, the Data to Everything platform. Splunk helps organizations worldwide turn data into doing. It's time for data to be more than a record of what happened. It's time to make things happen. Learn more at Splunk.com or by clicking the link in our show notes.
Jon, welcome to the show.
Hey, great to be on the show, Chad.
Jon, you're calling in from New York. I saw a little bit of your screen there. You have some music equipment in the background. You're calling in from a beautiful sunlit apartment. How are things out there in sunny New York?
Well, we are under lockdown, so life is weird. I've set up my apartment as a home office. My entire living room has become desk space and computer servers. And so definitely a change, but I've kind of settled into it. There are some aspects of this working from home that I'm going to miss. I think I'm working longer hours than usual, and I don't lose the time on the commute. But I miss hanging out with all of the people that I work with, so it'll be nice to get back to that.
Yeah, I couldn't agree more. The social distancing has kind of helped everybody filter what they appreciate and what they don't miss. And, I think everybody's had some time to think, and I'm excited to get back out there. Jon, you are the chief data scientist, and you're also a #1 best-selling author of a book that we will jump into in this interview. When you're introducing yourself and talking to some folks about what you do, what your passions are, how do you usually go about that?
Great question. I don't often have people come up to me and ask, what are you passionate about? But I think I do have a bit of an answer, which is that the world is changing incredibly quickly. And a huge part of this is facilitated by the ease with which information can travel all over the world, be stored cheaply, and then be processed in some kind of thoughtful way by machines. So the amount of data on the planet that we have stored doubles every 18 months. So however much data there is on the planet today, 18 months from now it will double, and that kind of exponential growth has been happening for decades and is expected to for the foreseeable future. That huge amount of data, lots of it is noisy, but some of it is meaningful. And machine learning algorithms are particularly adept at identifying meaningful patterns, meaningful signals from amongst all of the noise. I often like to think back to a time before the Industrial Revolution. So if we look back 150 years ago, 99% of people were involved in farming, kind of for subsistence, just to survive. Only a few percent of people were literate. A huge proportion of people died in childhood. And just 150 years later, thanks to automation of some tasks, now in the United States, for example, instead of 99% of people involved in agriculture, it's the inverse. 1% of people are involved in agriculture. And it's the same thing. Instead of the vast majority of people being illiterate, 97% of people being illiterate, now it's only a couple of percent that are illiterate. And so we've had these huge changes facilitated by mechanical tools that allow a relatively small number of people accomplish a huge amount. Over the coming decades, we will continue to experience this kind of change that we've already been seeing for the past few years, facilitated on cognitive tasks, where data and models that approximate the way that people think allow the drudgery of human tasks, human cognitive tasks, to be increasingly automated so that people's time frees up for creative, interpersonal aspects of their work, and ideally also frees up a lot more free time just for leisure activities.
This is so exciting. And I'm glad you took it in this direction too, because often when people get worried about, jobs going away, they forget this has happened already, several different times in our history. And this next time or this next transition could possibly be a golden age. Is this kind of something you see at a high level?
Yeah, I mean, I would say quantitatively, we already are in a golden age. There's tons of room for improvement. There is still tons of unnecessary disease and hardship that people all over the world experience, particularly outside of the Western world. However, quantitatively, across any kind of metric that you look at, whether it's in terms of lifespan, quality of life, these things like literacy, amount of free time in a week, all of these things are markedly better than they ever have been in history. And I think that we're set for that to continue going forward.
When it comes to data science, machine learning, and artificial intelligence or augmented intelligence, however you want to think about that, when did these subjects first get on your radar and how did you start to get involved with them?
Sure. Yeah, I guess I've always been working with data. Even as an elementary school student, I had a propensity towards the math classes and the science classes. So then through high school, continuing to specialize in those kinds of things, computer science, statistics, mathematics, and then doing that through my undergrad, doing a PhD at Oxford, specialized in applying machine learning techniques across a large number of compute clusters, so like a supercomputing cluster, in order to be able to identify patterns in very large medical sciences data sets, such as brain imaging data sets and whole organism genetic data. And so I've always kind of been doing this. It's just that in recent years, following that same kind of thing that I was describing earlier, where every 18 months the amount of data doubles. And so that means the number of tools that we have, especially the way that they're shared globally, typically freely through open source code repositories, there's just so much more that any individual like myself can do today. And now this field of data science has been coined. But people have been doing data science-y type things for decades. They might have been called a statistician in the past. But so I've been doing all these things kind of forever, and now it's coined as a specific field, data science, and I'm very lucky to kind of have this natural desire to be thinking about the world in terms of sampling data from population distributions and figuring out how these data can be linked together to do something meaningful and hopefully something helpful for people.
Sure. Jon, the show is called Hidden in Plain Sight, and one of the things that we focus on are just the problems or the emergent solutions that, with data analysis, machine learning, things like that, are often hidden in plain sight. So are there any examples of your favorite problems, whether they're in recruiting and retention or the workplace at large, where you feel like the answers were just hidden there and that they were obvious after the fact?
A lot of my clients are global corporates that get millions of job applications a year to thousands of different roles. They have too many data points. Their internal recruiters are overwhelmed by people who are interested in working at their firm. As this problem has grown, as the world is linked together by the internet, and these internal recruiters get flooded with exponentially more applications, the solution has historically been to look for keywords in the resumes. So an internal recruiter at a big corporate might say, okay, I've got this job opening. They're looking for someone who can write in Python code or in Java code. So then they do a keyword search to look across the 1 million people that have applied to their company in the last year and to search, just for those keywords, Python or Java, or maybe both of them together. Internal studies of people comparing the kinds of models that my company has built relative to that kind of keyword search has shown that using what we call a deep learning approach, which I can explain momentarily if you're interested in that,
Sure.
Using this kind of deep learning approach as opposed to a keyword-based approach, our algorithms surface 21 times more of the most relevant people for a given job. And so I think that gets at the kind of question that you're asking here, where there's this kind of thing where,
Sure, yeah,
there's a huge, they were getting 5% of the people out of their database that they wanted for a given job. And so in that sense, it was kind of hidden in plain sight. These people were there in their database. They were interested in working at the company, but by just doing a simple keyword search, tons of relevant people, the vast majority, were missed.
And is this due mainly to advances in natural language processing? Are you, identifying words and being able to zoom in on what words mean by the nature of the words that they're associated with? How is this process working, and how do you verbalize the explanation for this market improvement?
Yeah, exactly. You understand this very well, Chad. So we use something called word vectors, so we have a data set of hundreds of millions of instances of a given person being invited for a job or declined for a job. And so in each one of those hundreds of millions of instances, we have the whole natural language of the candidate's profile. We have the natural language of the job description of the kind of work that this person would have been doing in the role. And we train something called word vectors on all of these documents. And it's exactly like you described. It's a technique based on it's an early 20th century linguistic philosophy idea that was proposed by a guy named Ludwig Wittgenstein, pretty famous Austrian linguist. And it's this idea that a given word is the average of the words that tend to occur around it. The meaning of a word, it tends to be the average of the words around it. And so we can create a word vector by looking at all of the words across these hundreds of millions of documents, seeing what words tend to occur around it, and assuming that the word in the middle is going to be the average of the words around it. We can create this rich, high-dimensional word vector space. So if you think about it as like a three-dimensional space, because that's the best our brains can do, then there's 3 coordinates, say an X, a Y, and a Z coordinate that represents the meaning of a word. So the location of the word represents the word's meaning. And so words that are nearby in this cube that you're imagining to any given other point in the cube, these are all words that are going to be very similar. So common misspellings of a word will show up in the exact same place. The British or American spelling of a word will show up in the exact same place. synonyms will end up very nearby. And so by having spaces like this, and with computers, we can have these word vector spaces be much more high dimensional than 3 dimensions. It's very common to have them be 50 or 100 dimensional spaces. And as we move through that space, meaning changes gradually. So if we start at any given point in our word vector space and we move away from that point in a given direction, we might say, move from people who are applying to an extroverted type of role or an introverted type of role, or it can be highly granular where we're talking about moving in a direction in one space could mean that we're changing from software developers who are great at developing the front end, the kind of click and point user interface, relative to a software engineer who builds the back end, the kind of algorithms in the background behind the scenes. So these word vector spaces are these incredibly nuanced way of encoding the meaning of language. And that's the starting point in a deep learning algorithm for us to gradually build up increasingly complex, increasingly abstract understanding of a given candidate profile or a given job description, such that the algorithm has this very gentle, nuanced representation of the quantitative representation of the meaning of the language associated with candidate profile or job description. And so this means that there's no sense of an individual keyword mattering. The algorithm will be able to understand the whole document and say, okay, well, based on hundreds of millions of cases that I've seen in the past, when there's a job description that means this, then candidates like X, Y, and Z will be the perfect fit for this kind of job.
This is fascinating. And not only does it liberate the time of recruiters and those in the hiring world, but it has to improve job satisfaction and job outcome. Are you able to measure this yet? Or are we able to start to get some examples of how natural language processing is improving the life quality of people?
Sure. So there are parts of that question that, yes, I definitely have information on, and there are parts that are fuzzier. So in terms of whether this makes life better for recruiters, absolutely. We know that companies that use our software that allow them to automate these kinds of searches, they are able to make placements markedly faster than through manual searches. We're talking like an order of magnitude. Like several clients of ours have said to us, we started using your software and we went from the entire life cycle of somebody coming into our recruitment system, us suggesting a role to them interviewing and getting hired within just a matter of days, and typically it takes weeks. In a number of instances, we've been told that our software has allowed our clients to make their fastest placements that they've ever had. So in some cases, they've been using it for a few weeks, and they'll say, we already in these few weeks have had our fastest placement of all time. And these are companies that have been around for decades in some cases. So I know from that perspective that it definitely makes life easier for recruiters, and a kind of a cool thing that we do. So everything that we've talked about so far, you kind of have this idea of a recruiter kind of coming in and manually looking for the right person for a given job opening that they have. However, we've built something that kind of works like the Facebook newsfeed, where a recruiter can sit down at her desk any given morning or at any part of the day, and she's presented with suggestions, with these tiled suggestions ranked from the most likely, so right at the top of her screen, in the same way that when you log into Facebook or Instagram, you get suggestions of the content that you're most likely to be interested in. And then as you scroll down, there's some other stuff that you may be less interested in. In the same way, we at the top of this person's newsfeed, we provide them with the candidates that are the most stellar fit for a given opportunity. And then the recruiter can, in real time, within the platform, they can message that candidate, they can message the employer, they can phone either of them, they can say, yes, this was a good option, nah, this wasn't what I'm looking for. And then the algorithm in the background, based on that feedback of whether this was a good fit or not a good fit, will go back, and the next day, when the recruiter shows up at her desk, her newsfeed will be further refined in the same way that when you like something on Facebook, your feed gets better refined. So from that perspective, in terms of the recruiter's life being easier, I'm confident that our tools do that. With respect to your other question of what long-term outcomes, I don't have the data yet. It's really difficult to do that kind of thing. I love to think, and it's part of what motivates me every day, that we're therefore getting better people in the jobs who are happier for a longer period of time, but we just haven't been doing this long enough. I don't have good outcome data to let you know about that.
Sure. It seems like a meta theme around better NLP and better algorithms would be better communication, right? Human communication is very, very difficult. And, words mean different things to different people based on the life experiences that we bring to those words, among many other things. So I think it's just a really exciting time in general, because who hasn't felt the feeling of, I really, really want to communicate with this person better, but they're just, all these hangups. So hopefully machines can help us bridge that gap and start to collaborate more effectively there. Jon, in your book, you talk about generative adversarial networks, GANs, a bit, and you introduce the concept by bringing up the fact that some of these networks have been used to create machine art. Could you tell us a little bit about these networks and what they are?
Sure, yeah. So my book, Deep Learning Illustrated, I try to introduce people to the range of applications of modern deep learning approaches. So, machine vision, natural language processing, complex sequential decision making, and I think one of the most fun topics covered is exactly as you're describing, is this idea of having machines generate art. And generative adversarial networks are by far the most sophisticated and successful tool at doing this. So whenever you hear about deep fakes, whether it's a still image or a video, and notwithstanding how those deep fakes are often used in nefarious ways that I certainly don't approve of, but anytime you hear about those deep fakes, 100% of the time they're using a generative adversarial network to do that. And these are a really fun application of deep neural networks. So the idea with a deep neural network in general is that you have many layers of what we call artificial neurons or artificial brain cells. So each one of these artificial brain cells is designed to loosely mimic the way that a biological brain cell works. And in an artificial neural network, we link lots of these artificial neurons together in the same way that lots of brain cells are linked together in a biological neural network like your brain. And inspired by the way that the biological brain works, so when you look at something, the first layer of brain cells in what's called the visual cortex of your brain looks only for straight lines at specific orientations. And then a second layer of brain cells can recombine those straight lines into curves and corners. A third layer of brain cells can convert those curves and corners into even more complex, more abstract representations, until after several layers of this kind of processing, you can have brain cells that represent some very specific visual idea, like what your grandmother looks like, or what Oprah looks like, or whatever. And so artificial neural networks, deep learning neural networks, work the same way. And that's where the deep learning name comes from, is that we have layers of these artificial neurons where the first layer looks for straight lines, the second layer looks for curves and corners, the third layer, the fourth layer, it gets increasingly complex and increasingly abstract until we can have a deep learning network that can guess, given this image, I predict that this is Oprah Winfrey or whatever. So in a generative adversarial network, we have one network like that it plays the role of a detective. And so that neural network, it becomes a specialist at telling real images from forgeries. So let's say that we're training our generative adversarial network to be able to create fake celebrity faces. So our training data set would then consist of millions of high-resolution photos of celebrities' faces that were scraped from the internet. This detective part of the generative adversarial network will become specialized at telling real celebrity photos apart from fake ones. Now, where do the fake ones come from? Well, the fake ones come from a second deep neural network that is the adversary of the detective. So this adversary is a forger. And this forger, in the beginning, creates absolute garbage. It just creates gray noise. But through an interplay with the detective, it starts to learn, okay, what kinds of things can I do? What kinds of images can I submit to the detective that will trick the detective into thinking that this is a real one? And so the forger becomes better and better and better at producing images that trick the detective into thinking they're real, while the detective becomes better and better and better at distinguishing real from fake. And so this interplay back and forth, eventually the forger becomes capable of producing extremely compelling fakes of whatever training data set you have.
This is so interesting for a number of different reasons. And the Google researcher you say in the book that kind of stumbled on and helped develop this software thought it was the most, one of the most important things that had been developed in quite a while when it came to this field. And there are many different, implied uses and uses that are TBD here. But when it comes to open source software or ways that people can get started experimenting with generative adversarial networks, what are some that you recommend? You have some recommendations here in your book. Are there any similar to like MuseNet or GPT-2 where you can get started fairly easily?
That is a great question. So first, I think that quote, that researcher, I think that is Jon Krohn, the head of Facebook AI research. But that doesn't really matter. The important part of the question is whether there are tools out there for allowing us to build GANs easily. So in my book, there's open source code associated with it. And so you can find, by looking at my website, and we'll probably talk about that at kind of the end of the podcast, through there you can get to the GitHub repository, and there is what's called a Jupyter notebook for generative adversarial networks. The notebook is called Generative Adversarial Network. This has a model architecture in there already built for you. All that you need to do is change the training data. So in the book, the example that we use is hand-drawn cartoons. So we extract this data set from the internet of cartoons drawn by people playing something like Pictionary. And that game is fun in and of itself. It's called Quick Draw. And so you can Google Quick Draw game, and it prompts you, just like Pictionary, to draw something, draw a sailboat, draw a banana, or whatever. And then a neural network, just like the one I described for detecting real images from fake ones in a generative adversarial network, exactly that same kind of neural network will then work in real time in your browser to guess what you're drawing. And the objective is to be able to draw something so that it guesses correctly. And wherever it guesses correctly, those cartoons go into a database. And so then you can download these cartoons that people have drawn, and you can get 200,000 pictures of sailboats that people have drawn, cartoons of sailboats that people have drawn. And in my book, you can then use all those hand-drawn pictures of sailboats to train a generative adversarial network to be able to draw fake sailboats. And that architecture is highly portable. So, we use it for these cartoons because they're relatively small. You can train a neural network in a few minutes to be able to create these kind of fake sailboats. But if you wanted to use a more sophisticated image, like high resolution celebrity face photos, then you could absolutely still do that with the same model architecture. It would just take longer to train.
Very cool. And one of the other concepts that you bring up in the book that I'd love to get your take on is you mentioned that once an AI capability becomes commonplace, for example, recognizing handwritten digits, the AI moniker is typically dropped, and then the goalpost of the definition for what AI is begins to move. This is kind of involved in the higher level pursuit of defining intelligence. So could you tell us a little bit about that and how we can, as humans, maybe not be as worried about AI replacing us as maybe thinking about AI expanding our capabilities?
Totally. That's a really great question, Chad. So today, every single application of what we call artificial intelligence is something more specifically defined as artificial narrow intelligence. So this means that the AI, quote unquote, is capable of automating some kind of decision making in a really narrow domain. So, the algorithm that we talked about earlier that we build in my company, like matching candidates to jobs, we can train that on hundreds of millions of examples and have a candidate to job matcher that works very well. So on this narrowly defined task, we can have a successful AI algorithm. But if I took that code, that model, and tried to apply it to even something, only vaguely related, like analyzing the transcripts of an interview conversation and predicting the candidate's fit for the role, it would have no utility for that whatsoever. It would be completely useless. So as you take an algorithm that's trained for a very narrow task and try to apply to something else, this complete incapability, it shows you the limitations of algorithms today. And I think what people worry about is a theoretical idea of something called artificial general intelligence. So this contrasts with artificial narrow intelligence. This artificial general intelligence, it would be able to sort resumes and job descriptions. And not only would it be able to analyze the interview transcripts and predict whether somebody would be a good fit for a job, it would also be able to translate that document into another language. It would be able to hold a conversation with you in a way that you felt it was a compelling conversation. It would be able to drive you to work. It would be able to beat you at chess. It would be able to rebalance your stock portfolio. So an artificial general intelligence is this idea of a single algorithm that could do all of these different things. So it approximates the kind of thing that an adult human can do, a single adult person. And so I think people will when you hear about the term AI, which is a term that I try to mostly use in quotes, people think about the popular, the movie-driven, the Westworld-driven idea of AI, where it's something that approximates human intelligence. And today, there is not even a roadmap to getting to something like that.
Right. And it's more of this case where we haven't yet explored the power of adding the best AI algorithms to our own skill sets. So, I see a future where humans are, when you think about doing a task, there's an AI that follows behind you, almost like training wheels, to make sure you're, proficient at it and make sure that you don't fall, or, expands your capability. You talk about thinking about these GANs as creating like deep learning type paintbrushes for artists. And how do you see these algorithms starting to expand us instead of replace us?
Totally. So yeah, this idea of artificial intelligence augmentation, or AIA, I think is really cool. And depending on how you define it, we have tons of it happening already today. So, before recording this podcast today, I pick up my phone and I open the browser and I do a Google search for your name so I can learn a little bit about you. That Google search, that's an artificial narrow intelligence. That is a model that can look over a huge amount of information and surface for me instantaneously some information about you that if I didn't have that kind of tool available to me, I'd have to ask someone, or someone would have to, we would have had to have been introduced, and I'd have to learn about you that way. So there's all kinds of these examples of augmentation that we have today. Phones over the internet, computers over the internet, these allow us already to augment our intelligence in countless ways every day. More and more examples of that are going to happen as we go forward. So yeah, in the book I talk about an example there of if you're a specialist in designing fonts, which is like a really specific narrow task, you could use generative adversarial networks to make the designing of fonts way more interactive and playful. So you mentioned earlier in the podcast GPT-2. So a tool like GPT-2, this is a natural language model that is capable of creating really compelling paragraphs of information on a topic of your choice. And you can actually play around with that yourself as a listener if you go to talktotransformer.com. So you can go to talktotransformer.com, start a sentence, and then it will output a paragraph or two on whatever topic. And so I can imagine a future, and this is something we talk about and have even started building a bit ourselves, where we could have an internal recruiter who's just gotten off the phone with a hiring manager, and that hiring manager has described the kind of job description that they want to have, the kind of person that they want to hire. And then we can use tools like GPT-2 to allow the internal recruiter to type a few bullet points, and then the algorithm can make suggestions as to how the rest of the job description might look. And this could be highly interactive, where bullet by bullet or word by word, depending on how granular you want to get with the changes, you could then be selecting, okay, this bullet works, this one doesn't work, and have the algorithm interactively continue to improve and lengthen that job description for you. So this is an example of how, some task that might take a day, if you don't have a tool like this, all of a sudden that comes down to 10 minutes or half an hour. And a really cool tool that does exactly that kind of thing. So I'm an advisory board member to a company called Cynthia, Synthea. And so Cynthia is an AI tool that does exactly what I just described for legal documents. So if you're a huge law company and you have, these big law companies anywhere in the world, New York is a particular center for them. Any of these companies, they have millions of documents, millions upon millions of clauses. And a lot of the time you're trying to say a similar kind of thing. You're looking for a clause, you're looking for a confidentiality clause. And what Cynthia does is they have a thing exactly like what I just described for job descriptions, working for creating legal documents clause by clause. So there's tons of these kinds of applications that are going to make really repetitive, boring tasks easier and easier for people, so that work is more fun, leisure time increases, and year over year, these changes are relatively small. We're talking about efficiency gains of a few percent per person. We're talking about leisure time increases of a few percent per person. But you add that up over decades, and it's a huge change.
Yeah, it definitely sounds like it. And when it comes to learning on our own and becoming more self-aware and trying to improve every day, a lot of our listeners are executives and they're generally just passionate about self-improvement. I think the concept of reinforcement learning is very exciting because in my mind, many of us have been operating blindly. You can do the best you can to journal and try to track and quantify what you're doing. You can get really involved in the quantified self movement, but ultimately it's very hard to sum up all of the inputs and outputs of your life. So how do you see an idea like reinforcement learning being applied to human lives, and is this desirable?
Yeah, it's so funny that you think in this way. I think in the same way too. So reinforcement learning algorithms, this is an idea that's been around for decades, but deep learning combined with reinforcement learning has had a large number of breakthroughs over the last few years. And it's the closest thing that we have to an artificial general intelligence today. So there's a group called Google DeepMind based in London.
Sure.
And they're probably the world's leaders in developing AI technology using deep learning. And they specifically focus on deep reinforcement learning. And more specifically, what they are doing, and every year they generate more examples of this, they're creating algorithms that are slightly more general. So first they built the world's best Go algorithm that could beat the world champion Go players. So Go is the most popular board game in Asia. And they built this algorithm that could beat world champion Go players. Then a year later, they released a publication of an algorithm that they built that not only could crush that world's best Go computer, but could also, the same algorithm crush any chess computer and any shogi computer. So shogi is like Japanese chess. So they're slowly moving in the direction of this artificial general intelligence idea. And with any of these kinds of algorithms that involve reinforcement learning, we have to clearly define what we call the reward function. So when the algorithm is doing something simple like playing Tetris, well, in any Tetris game, in any Atari game like Tetris, there is a point score. And these arcade games that have been around for decades, all of them have point scores like that. And so we can train a deep reinforcement learning algorithm to maximize its reward, maximize its point score. With something like you were just talking about, with somebody's whole life, defining this reward function very clearly in a way that won't have unanticipated side effects could be tricky, but I think it's a really good idea. I think at first you might want to do this in a more narrowly defined way where you say, I'm a journalist and my goal is to write as many words as possible per month. Then in that case, the reward function is how many words did I write per month? And you could use quantified self-type tools like, I don't know, I use rescue time on my computer and on my phone. And so it at the end of every week, it gives me a breakdown of minute by minute, how much I was in productivity tools or social media or whatever. Mm. And so you could use information like that as your predictor variable. How many hours did I spend in Microsoft Word this week? And then your outcome is how many words did I write this week? So you could start to see how there's this relationship, and you could devise an algorithm that I guess could optimize for that in your life, and gradually you could broaden out. And the key thing there is that you need to have some kinds of limits, because there's some kind of, from the algorithm's perspective, you should be spending every minute of every day in Microsoft Word probably, right? Right. But then there's some pragmatic things there that, so even in that simple example, even that narrowly defined example, we start needing to add complexity into the reward function, so that it isn't just trying to maximize that simple thing of word count in the really simple way of how many minutes you spend at Microsoft Word per week. So yeah, so an interesting idea there. I don't think we're ready today for a deep reinforcement learning algorithm to really drive all aspects of a person's life. However, as more and more sensors are introduced into our lives, as will happen over the coming years and coming decades, as 5G rolls out, as storing and processing data becomes cheaper and cheaper and cheaper and cheaper, there might be sufficient sensors around for us to do that kind of optimization. And some employers, like Siemens in Germany or like WeWork, they do collect data from their employees, from their clients in an increasingly comprehensive way to allow them to be increasingly data-driven organizations.
Yeah, and I think this is a challenge for philosophers and artists, where the reward functions that's where imagination really, really needs to come into play now more than ever, where whether you think about Plato's ideas of the good, the true, and the beautiful, I think we need to start getting creative with those immediately. Otherwise, they will be defined for us. Jon, when it came to writing the book and doing the illustrations and everything, what did you discover and what did you learn in the process that really surprised you or shocked you about yourself or the field at large?
I discovered that writing a book takes a lot more time out of my weekend, a lot more energy than I ever would have hoped. I mean, I was already budgeting for it to take a huge amount of time and energy. You might have had the same experience too. I don't know. I'm just so incredibly neurotic about, tortured, in the middle of the night about that comma I took out or put back in.
That's where I'm most bullish on, AI algorithms and things like that to help out, because the writing process feels like it never quite comes out like you're thinking in your head, right? So whether that's, we eventually get tools where we have mind-brain interfaces to help communicate better. There's just like this gap, right? Between when you're tapping with your fingers or you're trying to use verbal expressions of these small mouth noises that don't quite express what you're trying to convey. So it's like this never-ending frustration of, I don't know, for me anyways, it just feels like this never-ending frustration of it's never quite what I meant, but it's close.
Yeah, and that ties back to something we talked about earlier that I think is a fun idea, which is that in the future, when computers rule the world and are really doing all of the processing and we're just kind of their pets, they will probably think that our kind of word-based communication was so clumsy and inarticulate, where they might find those kinds of word vectors that I described earlier. So the way that a computer represents language is in this extremely nuanced high-dimensional space. So if it has a 100-dimensional space and it thinks of, okay, this very specific location in this 100-dimensional space, that is how I would like to convey love to my computer mate today. And she'll really get that. And that, our kind of use of the word love was just so clumsy in comparison.
Right. And I think this is a challenge for all of us. There's a great sci-fi book called More Than Human to think about, what does it mean to evolve and become more than human? And this integrating technology into our lives more, it's very scary. It can be very unnerving for folks out there. I kind of think of this as like an event horizon we're getting ready to pass through, where we don't know what's going to be on the other side. And the unknown is always, pretty scary. From a philosophical standpoint, how do you think about this transition? Are you in the like Nick Bostrom camp where it's pretty, we'll get to this around 2040 and who knows what's going to happen afterwards? Are you in an optimism camp? How do you think about this?
Yeah, I'm in an agnostic camp. I'm optimistic without any good reason. A really great summary blog post is by, do you know Tim Urban, who writes Wait But Why?
Sure, yeah.
Yeah. So he has a blog post on artificial intelligence. It's really long, and it's broken into two parts. It took me days to get through it. But it does an outstanding job of distilling down Bostrom's thinking, other philosophers today thinking about AI. And he does a great job of explaining how we're helpless to be able to predict what would happen if in 2040 we do succeed in creating an AGI. And a great kind of summary way of explaining this is if you think about the difference in intelligence between Homo sapiens and any other currently living species on the planet. So, I don't know, what's the next smartest thing? A chimpanzee or a dolphin or something? The gap in intelligence between us, if you think about that as like one step on a staircase of intelligence, an AGI that we build, and maybe the subsequent versions of itself that it can very quickly build, could quickly escalate into what philosophers call artificial superintelligence, which is an intelligence that is greater than all human minds combined. And so if you think about that one step on this staircase of intelligence between us and the chimpanzee, this artificial superintelligence could be 10 steps ahead, or maybe 100. And so in the same way that explaining partial derivative calculus to that monkey just one step down on the intelligence staircase is going to be an absolutely fruitless exercise. You will never succeed at it. Think about that even much, much, much bigger gap between us and ASI.
Right. And bit unnerving. However, the future is still unwritten. No fate but what we make it. I'll go back to Terminator to feel better. Jon, thanks so much for joining us. This has been awesome, and I've enjoyed getting your take on things. Deep Learning Illustrated is out now. The illustrations in it are fun, and you've done a great job illuminating these concepts. If it comes to one more takeaway or a final call to action that you'd like to leave our listeners with, anything you have there?
Yeah, so the way that I kind of end the book, and I guess my philosophy in general, is machine learning algorithms, as we kind of just alluded to, they can be used for good, neutral, or bad purposes, and could have a whole philosophical discussion on what good is or that kind of thing. But I think today there are specific problems that we face as a species. So climate change, probably one of the bigger issues that we are going to be confronting in our lifetimes. And So to the extent that listeners who are likely to be engineers or data scientists who are looking for something to do with their considerable talent, I encourage you to, where possible, look for opportunities to do something socially beneficial with your talent. And so maybe that's climate change. I have in the final chapter of the book, I have recommendations and resources for socially beneficial projects that you could think about getting involved with.
I love that. That is an excellent call to action. And Jon, thanks so much for joining us. And to everyone listening, we'll see you next time.
I'm Sophia Bush, and you've been listening to Hidden in Plain Sight from Mission.org. This podcast is sponsored by our friends at Splunk, the Data to Everything platform. In today's data-driven world, every company, big or small, new or old, is sitting on terabytes of unused, untapped, and unknown data. Splunk helps turn all that data into action. Using cutting-edge AI and machine learning, Splunk delivers real-time predictive insights that will help you on your mission to change the world. With solutions for IT, security, Internet of Things, and business operations, Splunk empowers people to make faster, better decisions and take action to get things done. It's time for our data to be more than a record of what happened. It's time to make